Thank you, Shiry, for like organizing everything and just all the hard work over the last like 3 weeks and for another week. It's been really great, and I think we all appreciate it. And Shiry is going to tell us about, I think, using artificial intelligence models for social behavior, dancing, and so on. So let's see what she has to
not
say.
today. No dancing.
No dancing today.
Right, we're gonna do a sound check because I learned from Allison that you must do one right before.
Okay.
Okay, so thank you. This is a hard act to follow. My mistake. I made the schedule. Never do this again. Okay, so I just wanted to say one word about why we're here. And I came up with this summer cluster to kind of bring together different people from different disciplines to hang out with each other, because otherwise we don't really hang out with each other. We just do that in very local circles. And I did this when I realized that in academia, we kind of are discouraged to do this kind of thing because it's very risky for people in any given field to talk to anybody else. So the idea here is to take time away from your everyday academic life and engage in conversation with other people, because even at the simplest level, we have to learn each other's lingo to start making connections and start realizing that we can help each other in answering these questions. And this is happening all the time. Like I had a conversation with Jack last week, and I was talking about reconstruction, and I was talking about 3D reconstruction from images, and he's like, oh, you want to do reconstruction from the brain? That's just strange. So it took us like 5 minutes to be able to resolve that. So let me tell you about my question. And I'd love to hear your ideas. And my question these days mostly is about social behavior prediction and what are the representations that enable it. And what I'm talking about when I say behavior prediction is this ability to observe someone else's action and be able to predict what they are likely to do. And off the top of that, to be able to actively plan what I should do in response. So this is kind of different than Allison's idea of computer vision as a model for pictures. It's really computer vision as a model for behavior and prediction in vision. And this kind of thing is useful in the savannah, but it's also useful in the urban jungle. So last week, thanks to Joao and Violica, we made friends with Waymo, and we went for a tour of San Francisco in a self-driving car. And in order to survive on the road, this is very fascinating. This car has to predict at every given moment what any other car and any other pedestrian around it is going to do. And then it should plan what it should do next. And it actually surprisingly does pretty well most of the time. I did not expect this. But when it really gets stuck is where it needs to do any sort of hardcore social coordination, like a little bit of aggressive, like if you need to be aggressive when you're blending into a line of cars. And sadly, we did not actually film this. And the reason why, and the other thing is like, if it sees somebody like a worker, like a construction worker, and the worker is like slow, that sort of thing, no understanding. And the reason why is that these cars don't actually have a good model of what these other drivers might do in these types of social coordinations. Okay, so how does behavior prediction work? And this is exactly what I want to ask. And what I want to ask is, what representations enable this kind of behavior prediction? We can ask this computationally, but we can also ask, what representations in the brain? And this is the kind of stuff that Nate is working on. What types of information should we care about to make these predictions? And there we go. And how should we make these predictions? Okay, so let's start with the representations. In language, predictive models have been a huge success story, and we know that the success of LLMs is enabled in part by the use of word tokens. So for example, a large language transformer might take in a prefix of words as context, and then it can autoregressively predict the next word in the sequence. Okay, but does the brain really need language in order to predict behavior? Both the cheetah and the car can make predictions without it. Surely we can predict behavior in video. But what should a visual prediction token be? So just to give you some context, I'm going to recap what I talked about in the first workshop. If you were here for that, you already know that we can think of a whole spectrum of possible options that lie between low-level and high-level representations. All the way on the left, we have pixels, and all the way on the opposite end, we have objects, like 3D objects. But of course, if you impose more physical constraints and object-level priors, you're going to have to pay less. Sorry, if you impose more constraints, you can pay less in order to do this processing, because you're going to have an easier life when you learn how to predict, because you need less data and you need less compute to do this. And in my last talk, I walked you through several different options of what we could do. And what I proposed is to learn kind of a 3D-ish representation. I am not a fan of this clicker. To learn a 3D-ish representation for images that can enable video prediction while you're respecting the physical priors of objects in the world. The idea was to take 3D Gaussian splatting that was developed for optimization for the 3D reconstruction of a single scene and put it into an end-to-end network over multiple scenes. And here we're going to take a masked autoencoder, and we force the decoder to output this nice mid-level representation of 3D Gaussians. And I showed that this is a really nice representation where good things emerge, like different levels of grouping. Okay, but for today, no pictures, deep mind. Okay, but for today, let's focus on the prediction of human behavior from video. And for humans, we now have 3D parametric models that you can use off the shelf, and they disentangle the human form into shape, joint rotations, and mesh parameters. And this is a nice low-dimensional set of parameters. It represents all people in all physically plausible poses, and we can just predict these parameters, which is cheap, easy, and doesn't violate physical constraints. Okay, so in effect for this talk, I'm going to focus on behavior prediction mostly in the space of 3D humans or 3D human objects. And that's going to be the representation that I'm going to use here. All right, so that's what I predict, but what should I perceive? What channels of information should I care about? Let's start with a simple example of human social behavior, which is communication.
A terra, il cavallo a terra, ho lasciato il cavallo a terra. Vuol dire, ho preso il re, io non posso pigliare né un 3, né un 4.
Ok, tocca a me giocare, fammi parlare.
Okay, this is pretty cool. I don't know Italian, and Pietro is not here anymore, so I have no idea what these guys are saying. But it's pretty obvious that the older man is not happy with the guy who's sitting next to him. And I can tell this just from his tone of voice and all this upset gesture that he's using. So this multifaceted face-to-face communication is the most effective form of communication that we use. For example, here's a cool finding from Sandy Pentland that shows that separate teams in an organization become more efficient in working together, so they go towards the blue, after they all started taking their coffee break together. So they can actually spend time talking to each other instead of just sending emails all the time. So all of you who are here in person, extra brownie points. So nonverbal communication is very human and it's very important. But what do AI systems focus on today, like these LLMs that we talk about all day long? Most of the ones that we've been developing are trained only on text. And text is great, don't get me wrong, it can do all kinds of things like write poems. But at the end of the day, they're never going to understand us because they can't take into account all the important things that we have to say in nonverbal ways. So what's missing? Well, first of all, what's missing is audio, because speech adds a lot of information that's not in the text. For example, here's a written transcription. It seems clear what it means, but there are different ways to say it that give it different meanings. Here's one way.
My best friend and my sister, I cannot believe this.
And here's a completely different way.
My best friend and my sister. I cannot believe this.
Language, even spoken language, is also not enough because some things we never actually say.
George, have you seen Morgan?
No.
He's been coming in later and later. Is there something wrong?
No, not that I know of.
Really? Well, make sure he signs this. Oh, look, George, if there's a problem with Morgan, you can tell me.
Morgan? No, he's doing a great job.
I understand.
George is saying one thing, but he's communicating something completely different in his motion. What his boss is taking away from it is not in the text, is not in the speech, it's just in the motion. So how do people interact socially and communicate? They use the content, the lexical semantics, the meanings of the words. They use their voice and all of its colorful modulations to emphasize what they're saying, and they use gesture motion to complement the spoken language. And as we've seen in the real world, the face-to-face signals, the audio, and the motions are central to human communication. But in AI, we currently focus mostly on text. In fact, when multimodal signals are used, they often are translated into a language-based embedding before we make predictions. So the reasoning is really done in language these days. So in contrast, I want to focus today on the audio and the motion. We tend to think that with lots of data and machine learning algorithms, we can predict pretty much everything, but this is actually a hard problem because the data is multimodal. There's audio and there's motion, and they're not synchronized. The problem is non-deterministic. So if I tell you something today, you might respond in a particular way, but tomorrow you might respond in a completely different way. So how should we predict anything here? Like there's really seems like there's nothing to do. Now, in our first workshop, we had Kim Stackenfeld and Kelsey Allen, and they were fantastic. They told us all about these amazing physical simulators. Here's one example where they can accurately simulate many objects and how they interact with each other as they are falling very realistically. Unfortunately, behavior prediction isn't physics. We can't just simulate it. Because I love it, this is a quote from Nate, which I really, really like, is that there's a latent variable here that we know nothing about. And that is the internal state of other people. So LLMs can't help us. Physical simulators can't help us. So I think the only way forward is data-driven. And thankfully, there's a real revolution happening now in how we can learn from data. And this revolution is unsupervised. Instead of hand-engineered representations, I use representation learning to learn directly from large amounts of data without relying on human annotations using large-scale machine learning methods. Now, doing this kind of data on multimodal, doing this kind of learning on multimodal data is going to lead us to better representations that are more aligned with how humans expect models to work and how humans expect the real world to behave. And of course, now we have the compute to power this kind of effort. All right, so maybe we agree that we need to work with data, but how should we do the prediction? One popular option is autoregressive prediction. So if you think about Misty Copeland here, if you want to predict what she's going to do next, all you really have to know is what she's done up until this moment. So autoregressive prediction takes as input a prefix of tokens as context. This is exactly what LLMs do. And at each step, it uses its own previous predictions to predict the next token in the sequence. So all of these inputs are not ground truth, but they're previous predictions from the model. But what if you want to take into account the other people that we're interacting with? So when you have two agents working together, you need to take the other person into account. This is not captured by the vanilla autoregressive model. So instead, what I propose is something that I'd like to call polyautoregressive prediction. So what we have is we have different agents. We have maybe agent 1 and agent 2 up to agent n, and we have information about them, maybe over time as context. And the task is to predict agent number n, given their own past, and all the other agents as they update their information in real time. So again, these are going to be the predicted inputs from agent number n. All these other inputs are just ground truth from everybody else. They keep on telling me what they're doing, and I keep on updating my state. And it turns out that this paradigm is pretty general, and it can capture many different types of prediction problems. So what kind of predictions can we do with this? For example, here's a project we're working on now where we're looking at videos of swing dance. And what I'm doing here is I want to take one dancer, let's call them Bob, as input, and I want to predict their partner, Alice, and I want to tell what is she doing based on this guy. So here are results. Like, we're going directly to the results on this prediction text. The top left is the ground truth video. In blue, you can see the input person, Bob. In pink is the ground truth output person, Alice. And once we start predicting, you can see the predicted Alice in yellow. Okay, first example. Second example, here's another example of something that we can do that I looked at, which is dyadic nonverbal communication. And the task is, given the speaker's speech and motion, no text, I want to predict the motion of a listener. Why do I care about this? Well, it turns out this type of active listening is a pretty central ability for human communication, and we learn to do this when we're really young. So here's a 3-month-old, and he's already an expert. And this is my cute video of a baby like Allison's.
Did you get something to eat? Huh? Did you get something to eat? Yeah. Oh, is it so tasty? Yeah? Oh, my goodness.
Where can we find data to study this nonverbal, detailed dance of communication thing? Because it doesn't rely on language, and we learn to do it so early in life, it would have been great to take inspiration from how the brain solves this before language emerges. And people have been trying to do these studies with babies and mothers for a long time, since the 70s. Here's a study from Treverthen in the 70s where he uses a set of mirrors to get a simultaneous capture of the mother and the baby. But there's just not enough of this in the lab data to do anything with modern machine learning techniques. What kind of data is out there where we have people talking to each other for hours and hours in video? Ideas? Anyone? Zoom. That's a good idea, but you're jumping forward. Okay, but first, before Zoom, there were just talk shows. Okay, and there's years and years of talk shows that we can look at. But there's a problem. Most of the time, people on talk shows, the way they're filmed, they're just looking at each other instead of looking at the camera. And as a computer vision person, that is very annoying because it's hard for me to reconstruct their faces very accurately. So we wanted to do this project. There was a student here. We hung out with Trevor for like 2 years. There wasn't data. And then the pandemic happened. Thank you, JD, for the, yeah. And suddenly these talks moved to Zoom. And this is fantastic for us because now we can go and scrape hours and hours of people listening to each other speak while they're facing the camera. And this is completely non-scripted, in the wild, real interaction between people. So what do? Given a pair of people who are speaking to each other, this is a real conversation.
It really is lovely. I mean, the thing is, my children are adults. They're being very patient with me.
We can extract the speaker's audio and facial motion by fitting a 3D morphable model to the face.
My youngest is 18. And my oldest one's like, Peter is, what are you, 45? My oldest boy. No, your oldest boy. Oh.
We predict the motion of a listener.
He's 21. My daughter is 24, right? She's going to be so mad that I had to guess. She was 20.
And we can also synthesize an actual video to give you a better sense of what this looks like.
24, and we're kind of having to get out of their way. They deserve to not have us on, hovering over them all the time. Yeah. They're really quite self-actualized.
This is a completely synthesized listener video, and the input is the speaker, motion and audio. And you might have noticed this is also a completely different listener because we do this cross-person. I can predict somebody else from the data set, not necessarily the original one. So this is a non-deterministic problem. There could be many different possible responses for any particular speaker.
You're standing on that stage and all you hear is the echo of your voice because there's no one there.
Nobody there.
No one.
How should we model all of these possible answers? Well, here's a seemingly crazy idea that works in practice. which is to use a discrete code book of motion elements that we can then put together to create any sequence of motion like Lego blocks. And at the time that we did this work, this idea was around and it was explored with language and pixels with very good results. But it's not clear why it should work for motion, which seems like a very continuous signal. Well, conceptually, it makes sense that gesture contains atomic motions. And for inspiration, we can look at Laban notation, which is a notation that was invented to capture dance motion by a Hungarian choreographer named Rudolf Laban. And it's very similar to musical score. The idea is to record the position of the body, the pattern of the steps, and the way in which movement should be executed. Should it be forceful, or where should the accent be, etc. So in essence, this system breaks down dance, which is very continuous, into discrete atomic motions that are easier to write down than the continuous original motion. And the reason is because there is a set dictionary of these things, which is exactly what we want, right? So what are we going to do? Given a continuous motion segment and a codebook dictionary of atomic motion elements, we can divide the input motion into temporal patches. We map each patch to the closest, most similar atomic motion element from the codebook, and then we record the index of that element. So now the continuous input motion can be simply represented as this discrete sequence of atomic indices. A codebook is a nice representation because given an input motion sequence, we can design a predictor that predicts a distribution over the codebook elements from which we can sample an atomic motion from the next time step. And then we can train the predictor with a classification loss instead of a regression loss, which is a much easier optimization to do. And we can easily use now a transformer as the predictor because transformers work well with discrete tokens, not so much with continuous ones. And they're very good for this task because they are very good at modeling long-range temporal correlations in the input data. So in practice, we took VQVAEs that were developed for image synthesis and we extended them to sequence and to motion synthesis. And how does this transformer use this codebook dictionary for prediction? In exactly the same poly-autoregressive prediction paradigm. So from the speaker, now we take a multimodal input, which is motion and audio. From the listener, we take the motion of their past, what they did before. We do that a little bit for context. And now we start predicting the listener motion from these inputs, which we then can take in, condition also on the speaker, and keep going on and on. Exactly the same framework as before. How do we evaluate this? Well, there's not really a single number. Instead, what I want to do is I want to see that the output motion that I produce is realistic, diverse, and is also synchronous with the speaker. So I kind of have a whole benchmark of different numbers that we can use to get these different axes. But the metrics are only half the story here, and this is for Guillaume with the wiggling finger. Since we're trying to generate motion that can be used for communication with humans, we want to make sure that humans find it compelling. So I can ask humans, what do you think? Can I pass the Turing test? And here I'm showing the percentage of time the human evaluators prefer our result over some baseline, and I'm comparing two baselines and the ground truth on the x-axis. So what do we find? We find that people prefer our result over the strongest baseline, over the strongest ablation, and most importantly, most interestingly, is that they can't really tell whether the motion was generated by our agent or by a human. Okay, cute baby video number 2. Where does this get us? We managed to model listening behavior with 0 lexical semantics. This is not bad. I mean, these babies, 0 semantics, no text, but it's all here already. The entire basis of human communication. There's active listening, there's turn taking, there's imitation learning, there's humor. It's like me and these Italians from before. No understanding, but I smile, you smile, that kind of thing. And I argue that this is a large part of our human interface. All this rich multisensory data is what the AI systems that we build need to be able to perceive, model, and react to in addition to language. And in this line of work, I wanted to show that it's possible to extract information from raw audio and motion. But sometimes we do want to say something specific, like tell a joke. And for that, we have language. So we did a follow-up project where we tried to do something crazy, which is to see how far can we get in this listener prediction task by taking as input just text from the speaker side. There you go, jokes. How do you do something like this? Almost the same as before with a little twist. What we wanted to see here is what would happen if we take a pre-trained large language model like GPT. And what we want to do is we want to squeeze any goodness out of the lexical semantics that are already baked into this pre-trained model. And this is in the line of work that Trevor was talking about maybe yesterday or the day before. But LLMs take in text, and they're trained to generate text. And we want to generate motion. So what do? The main idea here, which is kind of cool, is that we can take those Lego blocks that we talked about before, those atomic motion elements, and we can literally treat them like novel language tokens. We are going to learn to translate from English language to motion language. We're just going to fine-tune GPT to be able to do that. So now we can take in text from the speaker as input, and then we fine-tune GPT to spit out these new listener motion words, and then we can use the same polyauto regression to take back those motion elements as input, condition on the speaker, and keep on going. What does this give us? Well, now we can get jokes. So here on the left, there's the audio and motion input, and on the right, there's the only text input.
Comes through town the first time, and everybody finds out there's no P under any one of the three shells. Well, next time it comes around, people have a little.
And we can produce serious responses when it's really not appropriate to smile, even if the speaker laughs uncomfortably.
Because we have to be uncomfortable to have this discussion. And unless white people literally see these injustices, sometimes.
So far, so good. We can condition our behavior on someone else. But what happens when you have to take into account many other agents? For example, maybe in a basketball game situation, if we look at this guy who just got tackled, what does he need to take into account? What I want to be able to do is I want to be able to tell just by looking at the motion dynamics that these players are all competing with him and they have conflicting goals. But these players are all collaborating with him and they share a goal with him. And then giving all this information and the people who are right next to him, I want to be able to predict what he's going to do next. So of course, this is Steph Curry, so he's actually going to be able to pull this off, but we want to do this in general. How do we do this? No problem. There's no actual theoretical limit for how many agents we can take into account in this way, or on how much multimodal information could go into any one of these tokens that we use for prediction. So finally, a big open question that we're trying to figure out together with Doris Tsao and Nate Dolensek here is how do all of these predictive social mechanisms work in the brain? And thankfully, humans are not the only ones who socialize. So we can, of course, look at animals as well. And I'm not going to expand on this because I think that Doris is going to talk about this tomorrow, maybe. And that's it. That is my behavior prediction story and my questions. And to not do what I told everybody else to do, I also put up a bunch of open questions, which I think are very interesting in general for social prediction and social understanding. Thank you.
question.
Thank you so much. I'm curious about like the multi-agent systems. How do you perceive the discontinuity when we cease to represent people as different agents, and when we start to consider the group as one meta agent?
Are you saying that this happens for us as in our brain as humans, or do you say that?
Yes.
Yes. That is a very good question. We are not there yet, I think. So basically, really nobody that I know of in machine learning really does this, any sort of idea that you should be able to predict based on other agents. And so I think that is the first step. Once we can do that, then we should have a conversation. Okay, when do you do this switch? And I would be interested if you have like theoretical material on what we know how humans do this. So we should chat later. Yeah. Yes, Uli.
Very nice talk. It's only clarification questions. You say that basically you use the other agent ground truth, but I'm confused about the timing, because basically I'm predicting my next move. So how can I use the future move as an input?
So there's different ways that you can set this up. And this is actually in several of these problems was a little bit different in how we did it in practice. But that's a very good question. So for example, you can say, I can take, if I have time step t and I want to predict myself in type step t, should I treat this as a translation problem and be allowed to see what you are doing in types in the same time step for prediction? That's one setting. The other way you can say this is to say, no, I always only see past. So I know what I did until this point. I know what you did until time t minus 1. And then I want to predict myself one step into the future based on this. I think it's like a question like, how small your epsilon wants to be. It's like we talked about yesterday. Okay, there is now. But now doesn't exist because it was already the past. And I think you can take into account like our action perception loop and whatever and make sure that, But I think it's just a question of like, it's all the same as far as I'm concerned. Yeah. And you need to flip up the thing.
This is really elegant work, Shiry.
Thank you.
So Trevarthen tested babies using a discrimination method that babies are good at to see whether a caregiver's video was contingent to the baby's video.
Yeah.
And you asked your Amazon Mechanical Turkers whether they preferred one thing over the other. And I was wondering whether Trevarthen's method might work as well or even better. That is to have people rate contingency.
Like, how do you ask the question on Mechanical Turk? That's a good point. I don't remember what is the actual wording that we used. We can probably look at it. I probably have it in the paper. I don't remember if we asked whether it's synchronous or whether which one do you prefer? But you're right that the way you ask the question might make a difference. Yeah.
Right.
Yeah.
Because really that's what's so beautiful. That's the mid step between independent agents and dyadic phenomena, which I'm going to talk about a little bit later.
Right. If we had used the word prefer, the assumption would be that you can easily detect. We know that even the babies, but we know that we can easily detect when there is non-synchronous behavior and it's very jarring. Right. So that was an assumption, but you're right. Maybe we should, if we didn't, maybe we should ask that in a more specific, concrete way. Even though contingency is a very hard word, I wouldn't put that on Turk. I would try to say that in a more English
everyday way.
Yeah.
Thanks.
It was just a great presentation. I was curious what the granularity of the kind of the facial lexicon you were selecting on. And the reason I mention this, I'm thinking of this PNAS James Zoe and colleagues piece that shows that like in assortative mating, that like the genetically most positively assortative factor is microfacial musculature, right? So the idea is, okay, maybe it's just that people like people who look like them, or maybe it's that people who have the same facial musculature are able to tell stories about what's in the minds of others when they see very subtle smiles, twitches, winks, etc. So so one can imagine, better or worse mind reading as a function of the granularity of the kind of the facial vocabulary that you're seeing here. I'm just curious how you think about that. And
yeah, no, that's a great question, because in this work, the bottleneck for that is the morphable model that we use. And when you make that decision to go with whatever those people produce, like George here can tell you more about that. So in this work, I'm saying, okay, George and friends have made these morphable models. I am just going to use them. And they're not perfect, especially for facial. Even in this work, we see that it's not really expressive enough to capture everything. It makes the prediction much easier than using pixels directly and, or using key points. But there are issues with the expressivity. So in this work, I was like, okay, let's assume that we have a good model. Let's see what we can do with it. And then actually, we submitted this paper twice. In that process, the facial model, usually they come from Michael Black in Tübingen, got better, and everything got better, So, but yeah, that's like the limitation of using these models, that they don't always capture everything. But George is going to fix that.
Go, George.
Yes.
Awesome talk. Thank you. And very cool work. So I wanted to ask about an issue. So an issue that comes up often in passive learning, actually, when you're doing behavioral cloning with just a single agent, is that if you evaluate the agent on the distribution of the natural data, it makes predictions pretty well. But as soon as you have that agent interacting with a real environment, it does something that's slightly weird, and then it gets off the distribution of data that's seen, and then sort of everything falls apart. And I'm wondering if the same kinds of things would come up in this setting, because if you had a real dyadic interaction instead of just playing the ground truth video, the person would be responding to the responses of the system, and then the system would do something slightly weird. The person would change what they were saying, and would get off the distribution of natural human conversation. So have you thought about that angle, and do you plan to do any assessments in that way?
That is fantastic question number 2. You guys are good at getting exactly that. Okay, yes. All of this work was one-sided, and none of it is a cycle. And really, any sort of interaction is a cycle. There's a feedback loop. You want to model the whole thing. Yes, this is my dream, to be able to either build it myself or convince a student. The student that was worked on this was Trevor's student, and she just graduated before she agreed to do the engineering work that will take to make this real time. Like, really, you want to be able to put these systems in front of a human in order to be doing some sort of like test time training in the feedback loop. Yes. So yes, absolutely. Let's do it.
We have one last question.
This is sort of related to another question that was asked, but I guess, so from my experience, like everybody in my family is visually impaired, actually, which sort of makes picking up on sort of some of those micro gesture things that like seem important for this actually fairly difficult. But we're also all fairly musical. And so there's, I guess, a question in my mind with respect to these things is, how do all of these sort of like intermediate representations or like tokenization of things, like what happens in that? Like, what is sort of that as a function of actually sort of like the psychophysical characteristics of the input modalities themselves? Like, if you have something that's multimodal that's getting image input, but you sort of like change the acuity on that, does it actually change sort of like what like things are actually like going into that representation? Does it change the representation itself, or does it like actually just converge on something just using sort of like different things that are sort of being picked up on for determining that? So I guess that's like one spectrum of things, just from the sort of like, there is a diversity in human sensory input sort of resolutions in different modalities.
So this is more a question about the multimodal representation. And I think the advantage of using a real multimodal representation, which is not just based on language or one particular dominant model, is like Paul was talking about yesterday. You have information that is shared, you have information that is only in each of one of the modalities, and then you have synergy. And maybe if you are not, when you don't have access to one of the modalities, the nice thing is that this shared representation, where's Philip? Philip is here? No, Philip talks about this Platonic representation that you learn from all the different modalities. The idea there is that it's very robust, right? And so even if you lose one, you can still do noise correction with the other modalities. So that's the hope, really, with using multimodal data. Cool. I think it's time for lunch.
Exactly.
So today we actually have a shorter lunch break, and we'll be back at 1:15 with Igor's talk, I believe. Yes, I'm excited.